Hello good people, I'm going to continue talking about molecular polarity by demonstrating how to assign partial charges and draw dipole arrows. By the smiles on your faces, I can already tell that you are very excited about this. My first example will be the humble water molecule. The first thing I'm going to do is assign the partial charges. I'm going to do that by using the electronegativity table. Based on the values there, I can see that the electronegativity of oxygen is greater than the electronegativity of hydrogen. This means that the oxygen will be pulling on the bonding electrons more, and as a result, it will be partially negative. This means that the hydrogens will be partially positive. And now I can draw in the bond dipole arrows. Remember that a dipole arrow is pointing towards the partially negative atom. So in this case, the arrowheads will be pointing towards the oxygen, while the arrow tails are pointing towards the hydrogens. So the bonds within the water molecule are polar. But is water a polar molecule? Recall that for something to be considered a polar molecule, I need to have a clear positive end and a clear negative end, or a clear positive pole and a clear negative pole. And that is exactly what I have here. The oxygen at the top is negative and the hydrogens at the bottom are positive. This means that now I can draw an overall dipole arrow for the entire molecule. And once again, the arrowhead is pointing towards the partially negative end. The next example I want to look at is ammonia. As before, the first step is to assign partial charges, and I do that by using the electronegativity table. Based on the values in the table, nitrogen is more electronegative than hydrogen, which means nitrogen will be pulling on the electrons more, which means nitrogen will be partially negative. And this in turn means that the hydrogens will be partially positive. Now that I have the partial charges, I can draw the bond dipole arrows. And seeing how nitrogen is the more electronegative atom and has a partial negative charge, the arrowheads are pointing towards it. Is ammonia a polar or a non-polar molecule? At the top, I have a partially negative nitrogen, while at the bottom I have partially positive hydrogens. So once again, my dipole arrow could look something like this, with the arrowhead pointing towards the top. I'm going to look at one more example, chloroform. Chloroform is similar to carbon tetrachloride that we have encountered earlier, except now one of the chlorines has been replaced with a hydrogen. As before, the first step is to assign partial charges. However, in this case, I have to be a little bit careful. I need to compare carbon and hydrogen and then carbon and chlorine. I'm going to deal with carbon and hydrogen first. If I compare their electronegativities, carbon is slightly more electronegative, which means it will be pulling on the bonding electrons more. So with respect to hydrogen, the carbon will be partially negative. And this means that hydrogen will be partially positive. All right, now I need to compare carbon and chlorine. Chlorine has the greater electronegativity, therefore chlorine will be pulling on the electrons more. And so chlorine will be partially negative. And if the chlorine is partially negative, then with respect to chlorine, carbon is partially positive. This looks a little bit odd, because we have two partial charges on the carbon. But let's proceed for a moment. What would the individual bond dipole arrows look like? Well, with respect to carbon and hydrogen, carbon is pulling on the electrons more, so the arrowhead is pointing towards it. With respect to carbon and chlorine, chlorine is pulling on the electrons more, so the arrowheads will be pointing towards the chlorine. So what is the overall picture? Well, we could say that the carbon is pulling on the electrons from the hydrogen, but then the chlorine is pulling on the electrons from the carbon. Is this a polar or a non-polar molecule? Well, this would be a polar molecule. Once again, we have a positive end of the molecule and a negative end of the molecule. And so I could draw a dipole arrow that points downwards towards the chlorines. Finally, and for the sake of neatness, we could say that the two partial charges on carbon would cancel each other out, so I'm just going to remove them. Please keep in mind that for molecular polarity, we need to consider several things. We need to take into account the electronegativities of the individual atoms, we need to take into account bond polarities, and then we need to take into account the overall shape of the molecule. That is all for now, and I will see you on the flip side.